In the previous class, we discussed about APSWRJC law and we applied to derive formula for magnetic field due to a current loop. Now, we will compare the magnetic field produced by a current element with that of electric field produced by an electric charge. So, there are some similarities and differences between the two fields. One similarity is the electric field and magnetic field both are long range fields. It means you can see or you can see the effect of these fields, or the fields can be observed even at far away point from the sources. So they are known as long range fields. Another point is similarity is both are vector fields. Electric field is a vector field. Magnetic field is also a vector field. That is another similarity. Another one is both fields depend inversely. That is, the electric field or magnetic field have inverse square dependence of distance. That is proportional to 1 by r square. So we have seen in Coulomb's law and also in APSWRJC law the inverse square dependence of the field strength, magnetic field. And also the electric field. So, if you see the Coulomb's law and APSWRJC law, you observe the inverse square dependence of the field strength at a point from the source. So, these are similarities. Now, there are differences also there. Both here, if you observe, electric field is produced by a scalar source, that is an electric charge, whereas magnetic field is produced by a current carrying conductor. That current element is considered as a vector. So it is a vector source. Magnetic field is produced by vector source. Electric field is produced by a scalar source. That is one difference. Another difference is also there. That is, electric fields are in the radial direction. That is, along the direction of the position vector. Whereas magnetic field will be perpendicular to both the current element vector and the position vector. So, the magnetic field depends upon angle between the position vector of the point from the source and the current element. So, it depends upon the angle. Whereas electric field doesn't depend on the angle. So, there is no angle dependence in the case of electric field. So, these are the differences. So, there are some similarities and differences between the electric field and magnetic field. Now, we are going to discuss about another way of expressing APSWRJC law, that is known as Ampere's circuit law. But before going to discuss the Ampere's circuit law, we must derive one formula for the magnetic field produced by a very long current carrying conductor at a point from the current element. So, by applying APSWRJC law, we derive a formula and we make use of that formula to explain or to derive the mathematical form of Ampere's circuit law. So, that is like this. So, consider a very long current carrying conductor. So, carrying a current of say some I. So, we want to find out at a point P, which is at a perpendicular distance of S from the current carrying conductor. And the element you are considering, let us suppose this is the current element. So, if this length is say some L dash, let us consider this element as dl dash. So, we have taken a small elemental length of the conductor. A small element you have selected. Suppose that dl dash or dl prime is at a distance of r. That is, the point is at a distance of r from this, and consider this to be some theta. So, this is the position vector of the point from the current element, and we can put the arrow here. So, and the angle between the current element vector and the position vector, let it be alpha. Now, from Biot-Savart's law, the magnetic field produced by the current element of length dl dash carrying a steady current I is given by mu naught by 4 pi I dl sine of the angle between the position vector and current element by square of the distance. So, if you observe, if this is alpha, then you know this angle will be 90 minus theta, or from the geometry of the figure, alpha is equal to 90 plus theta. Hence, I can write sine alpha is equal to sine of 90 plus theta, which is equal to cos theta. So, in terms of angle theta, we can rewrite the equation like this: dV is equal to mu naught by 4 pi I dl cos theta by r square. Okay, now here our aim is to express this equation, that is dl and r square, in terms of this perpendicular distance of the point from the current carrying straight conductor. So we can change the terms dl and r square and can express in terms of this perpendicular distance. So let us see how to do this. Here the elemental length, instead of dl, we will be considering as say some dl dash. And from the figure, you know L dash, this is a rectangular triangle, and this is L dash, and this is L. This is S. So therefore, opposite side by adjacent side is nothing but tan theta. Hence L dash is equal to S tan theta. Therefore, dl dash is equal to S into secant square theta d theta. So that is one relation we want. And another thing is, from the figure R, if you observe, S by R is equal to cos theta. So this is the adjacent side. Therefore, S by R is equal to cos theta. So therefore, R is equal to, that is, S by R is equal to cos theta. So hence R is equal to S by cos theta. So therefore, we can write like this: R 1 by R square. So 1 by R square will be equal to cos square theta by S square. So inverse it, square it and then inverse it. So let us substitute for dl prime this value and for 1 by R square that. Then see what happens. So dV is equal to mu naught by 4 pi I dl instead of dl dash. So what I write is this S and secant S by 7. So here S secant square theta can also be written as S by cos square theta into d theta, because you know secant theta is inverse of cos theta. Hence, in the place of this dl prime, I can write S by cos square theta. S by cos square theta d theta. So that is in place of dl prime by, and of course here this cos theta term is there, and here this is 1 by r square is there. In the place of 1 by r square, I can write cos square theta by s square. So in the place of 1 by r square, here this is the denominator term r square is there. So for that, in the place of 1 by r square, means multiply with cos square theta by x square. Now you see cos square theta gets cancelled and one s gets cancelled. So what finally you get is mu naught I by 4 pi cos theta d theta. Now, since the wire is infinite length, to know the total magnetic field produced by the entire conductor, you have to integrate between the limits minus pi by 2 to plus pi by 2. So B is given by, so that is integral of mu naught I by 4 pi cos theta d theta sorry, S is there. Yes. So this S term is there. From minus pi by 2 to plus pi by 2. Because this end will be at infinite position, this end also at infinite position. So almost we can consider that is from minus pi by 2 to plus pi by 2. So this on integration between the limits gives you, that is mu naught I by 4 pi s. So you know the integral of cos theta is sin theta, and between the limits minus pi by 2 to plus pi by 2. So you know the sin pi by 2 value is 1. So 1 minus of minus 1, that will be 1 plus 1. Hence you will be getting it as 2. So on integrating this function and substituting the limits, we get a 2. Therefore 2 times. Hence what formula we are going to get? Mu naught I by 2 pi s. So this is the magnetic field produced by a straight current carrying conductor of infinite length at a distance r, or at a distance s, perpendicular distance s from the conductor. So this is the formula what we want. So we make use of that formula to arrive at the relation between the magnetic field and current in Ampere's circuit law. So this you can consider as an application of Biot-Savart's law. So that formula we take it as it is, and we will discuss Ampere's circuit law. So Ampere's circuit law is nothing but another way of expressing Biot-Savart's law. So both relate the source with the field they produce, but the method of expressing the relation is different. In Ampere's circuit law, we derive the relation between the magnetic field and the current by considering the closed path in the magnetic field and taking the elemental paths and summing over all such elemental paths in the magnetic field produced by the current carrying conductor. We find out the relation between the magnetic field and the current in the conductor. So we take the summation of the elemental paths in the magnetic field. Whereas in Biot-Savart's law, we consider the summation, or we put the summation of elemental lengths of the current carrying conductor. That is, we sum over the current elements. Here, we are going to find the sum of the magnetic elements. That is the sum over the elemental paths in the magnetic field. So there is a difference in taking the summation over the current element in case of Biot-Savart's law and along the magnetic field path in Ampere's law. So let us consider a straight current carrying conductor carrying a steady current I. Suppose at a distance r from this conductor, if you imagine the magnetic field, so it will be perpendicular to both the current direction and the position vector direction. But the locus of all those points at the same distance will be a circle. So it will be a circle. So it will be a circle. Now from our right hand thumb rule, you know the magnetic field will be along the direction into the plane of the board according to our right hand thumb rule. So this will be the direction of the magnetic field. So let us consider a small elemental length of the closed path. Now let us consider the dot product of V bar, and of course we consider the elemental length in the path as also a vector, and see that what happens? B bar dot dl bar. That is what we are going to expect. So we know this is equal to B dl cos theta. Here theta is the angle between the elemental path we have considered and the magnetic field. Both are in the same direction. Hence theta will be 0 degrees. So cos theta will be 1. Hence we can write like this, B into dl. But the magnetic field produced by a long current carrying conductor according to Biot's law is given by mu naught I by 2 pi. Yes, that is the perpendicular distance. Here the perpendicular distance is r. Therefore, I will write like this, mu naught I by 2 pi r. Then dl is this. So suppose it is making an angle of say some d theta here. We know d theta from the definition of angle r by radius, dl by r. So this is the definition of angle. From that relation we can write that dl as r d theta. So r into d theta. Suppose d theta is the angle separated by the elemental path at the center. So this r gets cancelled. So what we get is mu naught I by 2 pi into d theta. So this dot product is not dependent upon the distance of the point you are considering. Now, if you find the integral over the entire path, that means closed path integral of b bar dot dl bar. So over the entire closed path, if you take the integration of the dot product, that will be equal to mu naught I by 2 pi. The integral will be only for this angle. So closed path integral of d theta. Now you know, if you sum up these angles for this entire circular path, that comes out to be 2 pi radians. Hence this is mu naught I by 2 pi into 2 pi. So this gets cancelled. Hence we will be getting mu naught I. So closed path integral of b bar dot dl bar is equal to mu naught times I. So that is Ampere's circuital law. Okay. So we arrived at this relation making use of Biot's law. So we can also say that what is Gauss law to Coulomb's law? The Ampere's circuital law is to Biot's law. So we can find some similarities. That is how the Gauss law is related to Coulomb's law. This Ampere's circuital law is related to Biot's law. Now you can extend the same argument for any arbitrary closed path. So for example, I will consider a general, say suppose I will take different paths like this, some closed paths like this. So I have taken some closed path in any general manner. So let us suppose this is a closed path. So let us indicate this as say some A, B, C, D, E, F and so on. Now let us see how the Ampere's circuital law can be arrived using this general type of closed path. For the given closed path, suppose for the path, say we start here. See this AB and CD, these paths are perpendicular to the current direction. So therefore, this cos theta value will become 0. Because the angle between the radial paths, that is radial elements, so AB is a radial element, CD is a radial element, and there are several such radial elements. So due to the radial elements, the dot product, if you calculate, will be 0. So they don't contribute for this product. So only this arcs, this arc, this arc, this arc, like that. So only such arcs will be contributing for the dot product. So therefore, this B bar dot DL bar, so that is equal to for a path, say, let me take BC. If you say, then I can write like this: mu naught I by 2 pi. Let it make an angle of, say, some theta BC. So let us assume that this arc part is making an angle at the center of the current carrying conductor, some theta BC. Similarly, B bar dot DL bar, we take another arc. So let us say DE. So we can write like mu naught I by 2 pi theta B, that is the angle made by this arc at the center of the closed path or at the current carrying conductor. So like that, for every arc of the path, you can calculate the dot product like that. But due to all these radial paths, that is AB, CD, EF, etc., the dot product will be 0. Hence, I am not writing that. Therefore, if you find the integral DL bar for the entire closed path, so I have taken some closed path for this entire closed path. This integral is given by sum of these mu naught I by 2 pi theta BC plus, so I can take this as common, and theta DE plus and so on. So into how many number of such parts you have divided. So for each arc you can find out that angle. You sum up for all the elemental parts. Then you know, for any closed path, sum of the angles subtended by the arcs at the conductor, because it's a closed path, must give you 360 degrees or 2 pi radius. Hence, this is mu naught I by 2 pi into 2 pi. So this is cancelled, mu naught I. So that means, again, what you are going to get? The closed path integral of V bar dot dl bar is equal to mu naught I. So like that, for any general path, you can arrive at the same formula. So that is the mathematical form of Ampere's circuit law. Here, the closed path you are choosing is known as Amperian loop. So that is known as Amperian loop. Now, what is the use of this law is, if you have some sort of symmetry around the current carrying conductor, then you can easily apply this formula to derive the equation for the magnetic field. So, due to a straight current carrying conductor, what is the magnetic field at a point at a distance r from that can be easily arrived using this formula. So, it can be done like this. See. So, that closed path integral V bar dot dl bar. So that is equal to mu naught I. Suppose we are talking about straight current carrying conductor. So B is constant at every point if the path is a circular path of radius r. Then B, this integration will be only for this dl. And you know the current the dl bar direction and B bar direction is same. Hence the dot product will become VDL, simply VDL. So VDL, that is equal to mu naught I. And what is the summation of all the elemental lengths over that circular path? It is the circumference of the circle or the loop. So V into 2 pi r. is equal to mu naught I. Therefore, B is equal to mu naught I by 2 pi r. So, in that way, we can easily apply the formula, that is the Ampere circuital law, to arrive at the formula for magnetic field. So, we discussed in electrostatics how the Gauss law can be applied by using some symmetric considerations to derive the formula for electric field strength due to a charge distribution. Similarly, here by using symmetrical symmetry about the current carrying conductor, imagining the Amperian loops with certain symmetry, we can easily arrive at the expression or formula for the magnetic field produced by a current carrying conductor. So that is the application of actually Ampere circuital law. So it facilitates or it makes easy for us to derive the formulas or equations for the magnetic field produced by current carrying conductor, due to which the magnetic fields produced have certain symmetry. In the case of a straight current carrying conductor, the magnetic paths have cylindrical symmetry. So, like that, there are several examples in which cases we can derive the formula for magnetic field easily applying Ampere's circuital law. Okay.